Alright, so in this video I'm going to be explaining another important article with the title Higher Order Organization of Complex Networks. This paper in 2016 from Stanford. So networks are a fundamental tool for understanding and modeling complex systems in physics, biology, neuroscience, engineering, and social science. Many networks are known to exhibit rich lower-order connectivity patterns that can be captured at the level of individual nodes and edges. However, higher-order organization of complex networks at the level of small network subgraphs remain largely unknown. However, we develop a generalized framework for clustering networks based on higher-order connectivity patterns. This framework provides mathematical guarantees on the optimality of obtained clusters and scales to networks with billions of edges. The framework reveals higher-order organization in a number of networks, including information propagation units in neuronal networks and hub structure in transportation networks. So the most common high-order structure are small network subgraph, which we refer to as network motifs. Network motifs are considered building blocks for complex networks. For example, feed-forward loops have proven fundamental to understanding transcriptional regulation networks. Triangular motifs are crucial for social networks. Open bidirectional wedges are key to structural hubs in the brain. Open bidirectional wedges. While network motifs have been recognized as fundamental units, the higher-order organization of networks at the level of network motifs largely remains an open question. So you see the motifs and so here also you see the higher-order cluster. It is elegance neuronal network, the 4-node motif. So here they reviewed first the graph Laplacian for weighted undirected graphs and the graph cut and all those elementary things like this one. They relate the cut metric to quadratic form on L. All of them are just background. There's nothing new here. And then they define the network motifs. So the matrix B, so we define a motif on k nodes by a tuple. B is a k by k binary matrix, is a set of, and A is a set of anchor nodes. The matrix encodes the edge pattern between the k nodes, and A labels a relevant subset of nodes for defining motif conductance. In many cases, A is the entire set of nodes. And this one is the selection function that takes the subset of k tuple indexed by A. And set is the operator that takes an ordered tuple into an unordered set. The set of motifs in an unweighted graph with adjacency matrix A is this. A is the k by k adjacency matrix on the subgraph induced by the k nodes of the ordered vector. The set operator is a convenient way to avoid duplicates when defining M for motif exhibiting symmetries. So this is an illustration of network motifs throughout the main text. So they just generalize it from conductance to motif conductance. And this is how they do. Instead of dealing with nodes, we work on the motifs. For example, number of motifs. Instead of number of edges like this, now we are talking about number of motifs. Number of motif instances cut, or number of motif instances endpoints in S. So we formalize this when given a motif set M like this. Then, naturally, because now the fundamental unit is motif, so they define the motif adjacency matrix, also motif Laplacian. Instead of original Laplacian, they have motif Laplacian. Then they develop what is natural for clustering. So for motifs, this is motif-based clustering. You find the eigenvector of second smallest eigenvalue of this Laplacian, of course, motif Laplacian. And then you sweep over, take the argmin, everything that you know from spectral clustering. But now they did it for motifs. Also, Chigger inequality with the traditional, the original theorem is based on nodes, not motif-based. So they generalized it for that as well. So this is the motif-based clustering for finding several clusters. Because if your clusters are more than 2, we could recursively cut the graph using the sweep. For example, we could continue to cut the largest remaining cluster until the graph is partitioned to some pre-specified number of clusters. So this is by partitioning.